Thanks.
Well, now's as good a time as any, Mr. Newman. Take her down to periscope depth.
Yes, sir. Clear the bridge. Dive.
Stand right.
Greetings, everyone. Welcome to this discussion of relativity and Maxwell's equations. I'm joined here by my co-host, Lena. And so, Lena, you sent me an email.
Hi, everybody.
And you had some questions about time. So tell me what you had, your question, and I'll try to answer it.
So, I was like having fun on Reddit regarding a German series, Netflix series, Dark. I don't know if you have seen that, maybe not.
No.
Dark? No?
I've never seen it.
And someone on the subreddit recommended this book of Carlo Rovelli, Order of Time, and I started reading it. It is for lay people, not for scientists, but it is nevertheless difficult, and it literally destroys the basic intuitive perception of time. And when you read it, you just start asking, what the heck is time? So Carlo Rovelli, he mentions, he starts with Einstein's relativity of time, mentions also the Maxwell's equations. So my understanding on the topic is very, very limited, and it is based mostly on popular culture. So I suppose you have seen this epic science fiction movie, Interstellar? Sal? I do not hear you. You are muted.
Oh, I'm sorry. Thank you. I'm still learning my way around StreamYard. So
Have you
go
seen
ahead.
the? Mhm. So in this movie, Christopher Nolan, um, starring Matthew McConaughey, there is a planet in the proximity of a very, very large black hole. And on this planet, 1 hour is equivalent to 7 years on planet Earth. And when Matthew McConaughey returned to Earth, he was actually younger than his daughter. His daughter was older. And this is what exactly what Carlo Rovelli describes in his book. It is like a point in time space has its own personal time. And in addition, what is even more confusing is that time is not only slowed down by mass, by gravity, it is also slowed down by speed. But we know that speed, it is distance per time. And then it gets very, very confusing, because what is how do we really define time in how do we in Maxwell's equations, for example? Because in Maxwell's equations, we know that there is this time variable t. What is then t in Maxwell's equations? T is the time where exactly, and is it time for an object that is moving or not moving, or you know what I mean? Therefore, I have asked you all those questions. You see, I see here in the equation that we have this variable t. What is t?
Thank you for taking time to explain. And this is actually a very good question that is worth is of value to people listening and wanting to understand science. And if I could just say one thing, as I learned, this is a very interesting topic. What you have said is actually accurate to the best of our knowledge, and I'm showing a partial proof of how we derived that. But more importantly, we have experiments that show this phenomenon. A variety of experiments that have showed that we could slow the clocks down. We could slow aging down significantly. We've done it in particle accelerators. We've done it also to some extent with airplanes, and very importantly in GPS satellites, because the GPS satellite network, the clocks have to be very accurate because of their distance from Earth, and then also the velocity they're traveling. We have to adjust the ticking of the clock to account for these relativistic effects. So as amazing as that science fiction story was, there is more than a grain of truth. If we could hypothetically accelerate a human being in a spacecraft to those velocities, we could, in principle, get them to like make 7 years be 1 year, or 7 years be like someone might age in the spacecraft maybe one day, and it might be 7 years in Earth time. And so I'll review that. So thank you. I looked at some of Rovelli's work. You're so generous in providing me links. And I didn't hear of that scientist. The moment I read the book, I was astonished. I said, this guy's not a crank. He seems like very intelligent. And because I'm not a PhD in physics, but I had a master's in physics, and I'm just like, well, this book it's really written for someone who has a little bit of a master's degree background, because it starts to make sense to someone like that. Even though the language, I could tell he tried very hard to make it accessible. There are parts of it that were pretty technical, but I'm going to try my very best to boil down some of it, and we'll go over the experiments. I'm not going to go deep into the math because it's the only reason I would show a little bit of the math is just to show that how this isn't just made up science fiction. It's grounded in some of the stuff we use today. So I hope that'll be helpful. And so I'm going to try to walk us through. I made a slideshow presentation, and I don't know how successful I'm going to be with it, and we can revisit it. So this is the first, one of the famous experiments. It's been somewhat controversial. This is the Haffel-Keating experiment. And I'm going to show some of these. Let's see if I have a picture. I don't have a picture of the clock. Oh, goodness. Oh, here it is. Here are very precise atomic clocks on the Earth. I believe this is the one at the Naval Observatory. If it's not, the Naval Observatory here in the USA it's a ground-based clock. So these clocks are in the US, and I see Jeremy Martin's here. Thank you for visiting. We have a small crowd today, but that's great because this is such a difficult topic. I'm going to probably stumble through it, so it's not going to be very polished. So you asked me in your email, what is time? Like a lot of things in physics, we actually call them undefined ideas. That trying to define it perfectly is not going to work. It's just like if you take a word in a dictionary and you try to define it, well, you need other words to define it. And so you end up with if you look up one word in a dictionary and then it's defined by other words in that same dictionary, you get circular reasoning. So every system of thought has what they call undefined terms. We might even say time is somewhat undefined, but we can measure it, we can experience it. Although we can't completely define it, we accept it as true. So we have these very precise clocks like this one here. Can you see my cursor moving? This is I don't see it on the StreamYard. Anyway, these are cesium beam atomic clocks. And what Haffel-Keating did, these are two gentlemen. One of them's named Haffel, the other's Keating. I don't know which is which. They got small versions of this cesium beam atomic clock. They had two of them. They actually had, I think, a total of 6 clocks, 2 that were on the ground and 2 that were in the air on an airplane flying to the east, and then another 2 clocks on an airplane flying to the west. And according to general and special relativity, why don't I just read this? The Haffel, this is from Wikipedia. The Haffel-Keating experiment was a test of the theory of relativity. In October 1971, Joseph C. Haffel, a physicist, and Richard Keating, an astronomer, took 4 cesium beam atomic clocks aboard commercial airliners. They flew twice around the world, first eastward, then westward, and compared the clocks against others that remained at the United States Naval Observatory. When reunited, the 3 sets of clocks were found to disagree with one another, and their differences were consistent with the predictions of special and general relativity. So does that sound familiar to what you were reading or what you found on Reddit?
Yes. And so the Naval Observatory is actually on the ground.
Yes, and I think
then
these are,
the other 3 clocks.
The other clocks were on the airplanes. So one of the I'm going to show you
And they
something.
were not only.
I'm sorry.
Mhm.
I missed what you said. I
No,
interrupted you.
no,
I'm
go
sorry.
on.
Okay, so
No problem.
the
It is
idea
so
is.
that
Oh, go on. There's just a little delay, so I'll have to pause a little bit. Go ahead, Lena.
there is time dilation.
Yes,
So the point here is that the other clocks, they are not only higher above the ground, but they are also moving.
exactly. And here's the calculation. So there's effects based on motion. What we call kinematic is the effect of so the clock that was moving westward, the velocity caused it to lose time. And I haven't gone through the experiment in detail, but basically, the faster you move, the slower your clock will tick relative to one that's stationary. And this leads to some difficulties as to what it means to be stationary. But just suffice to say, something that accelerates. So, like when you step, if you're in a rocket ship in space and you fire your rocket engine, you can feel the acceleration. That means you're gaining in velocity in one direction. And if you keep accelerating, you have higher velocity. And at some point, your clock is going to be it's going to start to tick slower. And because the airplane was moving, they were able to get just a little bit of loss of time. So that I'm interpreting this. People can read the wiki article on the Hethel-Keating experiment. I could be getting this backwards, so apologies in advance. But my best reading of this is that the clock on the Earth was ticking at regular amount of time, but then the clock on the airplane that's flying eastward lost time. So this is, I mean, it's very slight. This is, I believe, in like nanoseconds. It's not very much. But hypothetically, if they went even faster, they would have even lost more time. Which, what I mean by lost time is that just like in the example of that planet, so one clock. Can you tell me the story then about how much time he lost, so I could relate to it?
It is so. This is called Miller's planet in the movie, and this planet, 1 hour on this planet was equivalent to 7 years on Earth. It is, of course, an exaggeration, but what is shown here in the eastward direction is that time has slowed down.
Yes, they
Or
confirmed
not.
it. Now I'll give you the formula. This is the formula that will tell you we can, if you give me the velocity, so 1 hour is equal to 7 years. Well, let's just start with something simple. If we get up to 0.7 times the speed of light, we can get it to be about a factor of 7. So we can make 1 year equal to, let's see, wait, I'm sorry, hang on. We'd have to get very close to the speed of light. It would be on this part of the graph here. We can make 1 year equal 7 years. So 1 year on the spacecraft or on this hypothetical planet would equal 7 years. We can do that. We can even make it so that it is 1 hour equals 7 years. I'd have to do the math. If you want me to, I'll try right now. I can try that because I kind of like the
Let's
math.
do it 1 year. Okay.
I could totally.
Literally means that 1 second in this 1 second on that planet was a lot of seconds on planet.
Exactly. So I'm just gonna let me see if I could do this. I'm gonna do a quick calculation, and I apologize to the reader here. What I'm gonna do is I'm gonna enter in so I have my little spreadsheet here. So we have, so I'll enter in like T0, and then we have delta T. And let's see if I try not to mess this up. I'm doing this totally on the fly. So V squared over C squared, B and C. So if we are at 90% the speed of light, so V squared, oh, I can just do it this way. Hang on. So V squared. This is great because you could see how I fumble through this. And so don't feel bad if you have to struggle too. So all I'm gonna do is I'm gonna just make the denominator here 1 minus V squared over C squared. And I'm just using just ratios. I'm not using the exact units. It'll work out. Just trust me on that one. So 1 minus 0.81. And then we can take, so the denominator, so that ends up being the denominator. Oh, square root. So I'm going to take the square root of that. The point, if we're at 90% the speed of light, the denominator is 0.435. And let's see. So delta T. Okay, now we can have a little fun. So if we're at 90% the speed of light, 1 second on the spacecraft will be about 2.29 seconds on Earth. So what I'll call, let me just to clarify. So we have old Earth time, and new Earth. So I'm just going to highlight. So old Earth, what's a nice color for old? I'm just going to color it so people can see. I don't know how to color the font. It's bad. Let's see. How can I color that? I should know. It should let me color that. I'm upset. I don't know how to color things. They're supposed to give me, oh, there it is. So we'll make that brown, and you want to make new,
yeah.
We'll make this green for new Earth?
Yes.
Okay. So let's say we want to make it 1 second and older. I mean, let's see. I got that backward. I'm sorry. See? This is why it's good that I go through this. New Earth, old Earth. I got it backward, Lena.
Yes.
Sorry. This is why, so this is a good exercise for me to kind of relearn. It's been a long time since I've done this. So it's, thank you for giving me the opportunity. So 1 second on New Earth time.
No, I thank you because
is 2.29 seconds.
Equivalent 2.3.
So if I increase the speed of the spacecraft or the new Earth traveling through the universe. Let's increase it to 95%. How about 99%? So one has to get to 99% the speed of light, and then you'll get stronger effects here where 1 second on the new Earth is 7.08, whatever, 7.09. Let me make this a bit nicer here. We'll just decrease. We'll decrease the. So 7.1 seconds. So now I can even make it even more. We can just keep increasing as we go closer to the speed of light. And now it'd be good for me to make this. As we go closer to the speed of light, we can arbitrarily make time what we call dilate. So you can even get it to a factor of over 2,000. Do you see how that works? So the question is, where did this equation come from? And that's the hard part. But the important thing is we have experimental evidence of this, and it actually does affect our everyday life. For everyone that uses GPS, we have to add this correction in for changes in velocity. So any questions? Does that help? It may not answer your question as to what is time, but it does show the relationship of how the clocks tick differently. I prefer saying it's not time, it's the clock that is changing. Does that help?
Yes.
So what this is, this formula, go on.
No.
Okay. So this formula is
so far it's clear.
Okay, good. So that's the easy part. That's not too hard. So you could just build a spreadsheet, and then you can kind of imagine how fast one would have to go to make your clock tick. So this is amazing that it says in the Bible a day is as 1,000 years, and 1,000 years is a day. We have kind of a principle of how this might be possible, even hypothetically. So continuing on, so that's the calculation. How this is derived is monstrously difficult, but I'm going to just for completeness, I'll point out a few other things. So this is for the effects of velocity on the clock. Gravity has an effect on it. This is from Wikipedia. If someone looks gravitational time dilation, this is a much more complicated thing, and it's complicated enough that even I haven't worked with it very much. I'm more familiar with this one, and you can see it's not. I mean, it just we were able to plug in the numbers within about 5-10 minutes and show how the clocks change. But the one that involves gravity is pretty intricate. Yes.
Didn't Einstein say that gravitation is equivalent to acceleration?
Yes, that's an assumption. I'm in the minority. I think Einstein is very close to being right on a number of things, but he's just a little bit off. And that's where it becomes very interesting for young Earth creationists, that where he might be just a little different. And so I'm going to cover a little bit more. So we at least see the thing with the variations in the clock based on how fast you're moving, and then variations in the clock based on whether you're experiencing gravity or not. When you have a lot of gravity, I think it makes the clock go slower. And when you're away from gravity, you tick faster. I could get that backward So apologies to our listeners if I got it backward. There is an effect of gravity. So this is Maxwell's equations
Yes.
of electrodynamics. So how can we derive this, where we get all this change in the clock based on Maxwell's equations? So the first thing is, what are Maxwell's equations? Maxwell's equations is as difficult as it looks. It has a lot of practical applications. For example, just like let's see. I'm trying to think of some everyday examples. There, practically anything that deals with electricity, first off, will be governed by Maxwell's equations. So a lot of the stuff we do, even with, like, let's say just very mundane, when you turn on a flashlight, or when you have electricity going through something, it deals with charges. And so the first of the equations, there are 4 of them here. The first one deals with electric charges, Gauss's law. And I'm not going to go into that's a simplification, what I described. This talks about electric flux. The next is magnetic, is the law for magnetism. And we don't have to go into all of that. The one that's interesting, that's very important, is the way we generate electricity. So like or motors. This one deals, this Faraday's law of induction. That means, like, when you take a wire and pass it through a magnetic field, you create electricity. That's how a generator works. So when if you've ever worked with a hand crank generator, like there are these flashlights you could just turn and it generates electricity as you're turning it. What's happening is you're taking wires and moving them through a magnetic field. So this is what that does. This one here, the Ampere's circuital law, that's the one that is probably really important, where we have changing electric fields creates changing magnetic fields, and that's pretty difficult. But where all that is leading, and I'm sorry, so suffice to say, if we didn't have these laws here, we wouldn't be understanding electricity, or we wouldn't be understanding light, or radar, or radio communications. So practically civilization as we know it would end if we didn't have this. So the fact that we're able to describe how radio waves and magnets and electricity and light work through these equations, we've been able to have modern technology. So what ends up happening is there's solutions to these equations that predict how light will travel through space. So this is, you can just imagine, like the blue here is the electric field within a light wave, and the red is a magnetic field. So you could see that the electric field changes over space. So just imagine a light wave traveling from left to right, and you can kind of see it here traveling. And it's actually built up with changing electric and magnetic fields, And so you have also like the wavelength of light there. So I know I'm fumbling through this, but it's partly because I haven't ever really taught it directly. So so maybe the takeaway is to be able to describe a light wave in terms of electric and magnetic fields. It proceeds from Maxwell's equations. Maybe that's the easiest. The thing is if we took this Maxwell's equations and we said, okay, what does a light wave look like? It's even more. Let's see if I have it here. Oop, I'm gonna have to switch gears here. There are these try not to get too bogged down in the math. One ends up having these solutions that they call the electromagnetic wave equation, and it gets just kind of hairy that they can predict. Let me see. So you see these equations here. It predicts the shape of. Let me see if I can get it up. It predicts the shape. You need all that math. All that math. I'll show you what all that math results in. We need all this math to be able to draw this graph. I mean, it took a lot of labor just to be able to draw this little sine wave here. That was just brutal. And I that's why it was easier. The beginning part of our topic was much easier than getting to this part. So, but do you sort of at least see what Maxwell's equations are? It helps us describe what the shape of a light wave. So maybe the easiest way to describe this is if we start with these equations and do lots of painful math that takes a year to study, we're able to see that we can make light waves that have this shape. Is that sort of okay?
It's okay. But as soon as I hear wave, then I'm, how to say, it's difficult for me because I cannot imagine what a wave is. A wave for me is something that something does, not that something is.
Oh, okay. Well, let me
But
see.
that's another topic.
Okay, let's see if I could show another picture. If I could show. So here's a picture of ocean waves. And you can kind of see it has that shape. You know, you could see if I could find a better picture. Let's see if I could find. Oh, wait. Let me see if I could find a better picture.
This picture is perfect. A wave is just a disturbance.
That's one way of thinking of it. I think I have a better picture. So there's like a pebble or something that's dropped in here, and you see these little ripples here. They actually are kind of like, if you just take a line through there, if you just kind of sliced it out, you'd see it has kind of the shape of, let me get rid of this picture. It kind of has the shape of this. Just think of the blue. You see that kind of that sine wave? So if you think of it as a disturbance is close enough, I think that'll work. So basically, what's really kind of painful in all this is when we look at the bottom line of all this nasty math, the final result is it predicts it predicts these little ripples. So after all that, that's the solution, is you get these little ripples that can be described as sine waves, or what we would call the superposition of a variety of sine waves. So the shape of this graph, by the way, is what they call a sinusoidal. Have you heard that term, like a sine wave? Let me see if I could show a sine wave.
Yes.
I'll show something more pure. This is actually really good because you're helping me to, as I'm fumbling through this, I'm trying to think of better ways to explain ideas. So because I might have hopefully a more polished version of Oh, what did I do? Didn't mean to do that. So this is the shape of a sine wave. It has certain statistical properties, but again, it's just like a ripple. So that's a sine wave. And one of the solutions to Maxwell's equations predicts a sine wave like that. Now, I'm sorry about the red here, but let me go back to that picture of the sine wave. So if we're just dealing with the electric field in a wave of light, it would look like one of the solutions to Maxwell's equations would be a wave like that. There are other solutions. We won't get into that right now. I'm trying to keep this simple. So that's basic. It took, I mean, this was a lot of work to get to the point where we could first build these equations, and these were derived experimentally and also mathematically. So there's a lot of difficulty. In fact, when Faraday did work on this, he actually didn't do a lot of math. He was just doing experiments and reporting results. Let me see if I could show some of Faraday's experiments. See if he had the actual equipment. It's actually kind of cute, some of the equipment he had. I'll show a picture of Faraday. So this equation here, it says Maxwell-Faraday equation. I'll show you the experiments. There's a picture of Faraday there. And so he had these little balances and he's playing around with electricity. And from these, you could even see like he has a little fireplace behind him. I mean, these were really tough experiments, and then they're deriving all this really cool science to develop Maxwell's equations. And then some of this other stuff took hundreds of years, I believe, to start deriving it. So this was not easy stuff. But anyway, how does this relate to time? Going back to time, somewhere embedded in, you could see it right here where it has t here. You could see it has a t here and a t there. So some of Maxwell's equations involve the variable t, and that's important.
Yes.
So now I'm just gonna. Anyway, so this describes. This is a fancy way of describing that sine wave you saw. So if you see this, the equation, one of the equations that describes it is this. That's a gross simplification. Someone's going to hammer me for saying that. It's actually a sine wave in 3 dimensions, but we don't need to go there. And anyway, so what ends up happening is we start with this equation. And we wanted to see what would happen if we had.
To say we have.
Say again, Lena.
Sorry, Sal. So we have 3, actually 4 dimensions here. X, Y, and maybe.
Yes, X, Y, and we have 4. We have X. You could see it.
Yeah.
Yeah, you could see the X, the Y, the Z, and the T. They're 4 dimensions. I actually don't like the fact that they make time a 4th dimension like space, but yes, there's 4 dimensions in the Maxwell's equation. So that's very astute observation. So these equations incorporate these 4 dimensions, X, Y, Z, and T. And you could, and just for the reader's benefit, I believe this is the Laplacian of, I don't need to go there. Anyway. So what we might try to do is we relate the observation of this light wave. If we saw the light wave, let's say that two observers were looking at the same light wave, but one of the observers is moving. We tried to see how it might be observed, and I'm not going to be explaining this very well because I don't understand it well enough to be able to explain it clearly. But what they said is that Maxwell's equations are invariant. It's already built into the equations that the speed of light will be observed. It'll always have the same speed whether you're moving fast or slow, the way you'll measure it. So it's a very strange property that if you have an experiment and your spaceship is moving really, really fast at 99% the speed of light, inside your spacecraft, if you measured the speed of light, it would be the same as it would travel whatever. It'll always be the same velocity. And let me just give you the velocity here. Sorry. Velocity. So this is a very strange property that's inside Maxwell's equations.
Strange.
So the speed of light is roughly 186,282 miles per second, or about 300 million meters per second. 300 million meters per second. So if we have instruments that can measure the speed of light. So the speed of light will always be the same, whatever your measuring device. So this raises some interesting paradoxes because your clock is moving slower if you're moving faster, but yet you're going to measure the speed of light the same inside your spacecraft, no matter what velocity you are. It's just a strange property. And so that's built into Maxwell's equations. Now, a little caveat here. I don't completely agree with Maxwell's equations, and it's known as an approximation, but it's pretty good. So this is a good place for a question because I know this is going to be strange. No matter how fast you are, you're always going to measure the speed of light at this speed.
I do not understand that.
Isn't that weird?
Because everything is relative to each other, and velocity.
Well, this is.
And velocity is actually.
Okay, what ends up happening is, what's really strange is that, remember, your clock is moving slower if you're moving faster. And so your clock will slow down just so. One way to think of this is in classical mechanics. Let's see, I'm trying to think of this. If you're driving toward a building at, say, what's this? I know things in miles per hour. How would you, if I said, in your country, what's the speed limit in kilometers? Is it in kilometers per hour?
$140 kilometers per hour.
Okay, 140 kilometers an hour. So the way one would think of it is if you threw a rock, if you dropped the rock out of your window at 140 kilometers per hour, the movement of your car will make that object move faster. And light is very different. You can't add speed to it. So, which makes it, I'm trying to think, this is why I'm going to have to review this discussion because you could see I'm stumbling through this because it's so strange. How can it be that the speed of light is always invariant? however you measure it. So that's why when you have a car that's moving 140 kilometers per hour, the light coming out of its headlights is still moving at this speed. You can't add speed to it. And I know that's very strange, but that's just that's what Maxwell's equations, the way that they're written, predict. And so I'm trying to think of ways we could not think of this classically, because when we think of things classically, if you drop a rock or you throw a rock and you're moving at 140 kilometers per hour, you have to add that velocity of your car, but light doesn't behave that way. And so there's a property of space that limits its imposes a speed limit on the light. It imposes a speed limit. So that may be kind of hard to think why there would be a speed limit to the light. It does change the property of the light, however, meaning when you're moving faster, you're causing the frequency emitted to be slightly higher, what we call blue shifting. And that's actually why, with some finesse calculations, the police can have a radar gun or a laser gun, what they call a LADAR. They can tell if someone's speeding. They can tell if someone is speeding, not because the speed of light's faster in their instrument, but they can measure the change in the frequency. So maybe that's another topic, just to start to see that. But going back to time, let me just try to close this out. And if we grind through all the math and we try to reconcile the observation of two observers, one stationary and one moving, we end up creating one way to resolve it so that it's what they call invariant. And I'm sorry, I'm just throwing out terms here, but this probably took a couple of years of math work. So what I'm just showing you, like in 1 minute, was like a couple of years by these famous scientists with great difficulty. And I'm just rederiving the equations here. But when you grind through it all, you end up with this thing called gamma. And it makes everything work out well. And that gamma, I'm going to go back to our slide here. That gamma is, show it here. That gamma is right here, this term here, or 1 over gamma. So that's how Maxwell's equations was able to predict it. I didn't do a very good job of explaining it, but that's kind of an outline of how they were able to predict it. So even before we had these experiments like the Heffel-Keating experiment, before that, we had made all these predictions, but we had no way of testing it so accurately because we didn't have clocks like the cesium beam atomic clock. But once we had it, we could actually test it. We could test if Maxwell's equations would predict that. And so what ended up happening is that was the prediction of special relativity. The more velocity you have, the slower your clock runs. And so we did this little exercise. So it took a lot of math to predict that, but the bottom line is actually not too bad. So I know I probably raised more questions than I answered, but I hope at least your understanding of time has changed a little bit. I would say I personally believe that there is an absolute time, but the phenomenon that happens is the clock slowed down. That's not the mainstream interpretation. The mainstream interpretation is that time actually flows differently, and I don't believe that. I think just our clocks tick change how quickly they tick. And whichever viewpoint one adopts, you'll get pretty much the same experimental results, minus some anomalies, which is what I'm interested in as far as young Earth creation.
So what I do not understand, how did Maxwell know that the speed of light is a constant?
I don't have an answer for that. Wait. Let me think back. I think when he originally wrote his equations, he was just looking at electricity and magnetism. It was not necessarily immediately trying to deal with light. So let me show the graph here. When he was formulating it, again, they were just doing experiments like Faraday here. And they're just compiling little relationships, one little bit at a time. And then with some great difficulty, they realized, oh, this predicts the behavior of light. So I don't think he started off with trying to connect magnetism and electricity to light. So the first thing that they were studying was electricity and magnetism. So even little children, they love playing with magnets. So that's the first thing. They're just studying magnets and how they worked. And then they were studying electric charges, like on a very dry day when it's not humid, we can get a lot of static electricity, like when you've probably seen the effect of static electricity, like rubbing cloth or something can develop static. So people were interested just in static electricity, and then they started building batteries and having other kinds of electricity, and then they started seeing things like magnetism. So when they started to combine magnetism with electricity, which Faraday did, he noticed that you could generate electricity when you move a copper wire through a magnetic field. I know that these scientists have special minds that they would even try that. It's like, let's see what happens when you move a wire through a magnetic field. And they were just curious. And so it developed this equation. And then they had some other experiments that led to this equation. So they had all these equations, and then they put them together, and then they realized, we can predict the speed of light. And that's how it actually began. So I don't think that they actually assumed that the speed of light was invariant to begin with. They just kind of built this up, kind of bottom up. And I think it was later that they said, let's just assume that it's invariant. I think there were some experiments that showed that. I'd have to go back into the history because sometimes the physics textbook don't really get the history. They kind of simplify it. It might be pretty subtle. But the important thing is most of our lab experiments show light is invariant. There have been a few that suggest that it's not. The speed of light is not invariant. It may change. And I've actually worked on some of those experiments. I'm not much of a mathematician. I kind of like to tinker. So that would be an interesting question. Have we found variability in the speed of light? And there have been some experiments that have suggested that. And that's that should be of interest to young Earth creationists, that the speed of light, there might be regions of space where it can travel very, very fast. So maybe to answer your question, maybe Maxwell is wrong, but he's mostly right. He was close enough to being right that we just generally assume that he was correct. He could be slightly off. And that was kind of that's the topic of my research interests. And by the way, there are a lot of variable speed of light theories now. There are a lot of them that weren't created by creationists, ironically. They're created by the mainstream. The problem is being able to create experiments that can demonstrate this. So I'm very interested in that. So your question again was, how did Maxwell know that the speed of light is constant? I don't think he knew that, and I don't think that that question is settled even to this day. But the equations we're looking at assume that it's constant. So like a lot of laws of physics, we kind of tinker with them, and as long as they work and help us build things and do technology, we'll accept it as true. But it doesn't mean there might not be some exceptions. So has that been at least a little helpful?
Definitely.
Well, maybe we could have another discussion, and I can you can email me some of your questions, and these are good questions because I really want to explore this. And so those mathematical derivations that you saw me kind of scrolling through, I'm trying to write an educational paper to kind of to teach how to derive those things. So we could actually take Maxwell's equations and construct that that Lorentz transformation, the one where we had our spreadsheet, and we could show how the clocks tick differently. Because a lot of the way they teach it in high school, understandably, it's just to give you that equation. They never explain where it came from because it's too complicated. But then even a high schooler could just say, okay, if I travel this fast, this is how slow my clock would be, which is really cool. But to actually get to that equation is pretty miserable.
So I still cannot understand the speed of light. How? What I mean is, you said when we travel with speed that is approximately near the speed of light in a spaceship.
Oh, I have. Oh, I think I can explain this. It just occurred to me. All right, when the speed of sound is generally constant, it's approximately constant at sea level, approximately. So it doesn't matter whether your vehicle, let's say you have a vehicle and it's making a sound like from its engine, or it's blasting its horn. Like when you have a train, how about a train? So when a train is approaching you, it has one sound, and then when it passes you, it has a different kind of sound.
Yes.
That's because the speed of sound is relatively constant. So it doesn't matter that if a train is moving at 140 kilometers per hour, the speed of sound that it's generating is still traveling at the same speed, but it changes the frequency. So the speed of light is kind of the same way as it's traveling through space. Just think of space as a medium, as an ether. And some people are going to hate me for saying the word ether, but it's a good way of conceptualizing it. A lot of people have dissed the ether, but there's kind of a revival of the idea of ether, and that's a whole nother topic. But if we just think of the air as like a medium for sound to travel, it'll always be that speed. And so when an airplane, like a jet fighter, passes the speed of sound, you can't hear it coming because it's moving faster than the speed of sound. But once it passes over you, you'll hear a sonic boom. It's like an explosion. It's ferocious. So the idea that so from the classical view, where we are having a car that's moving at 140 kilometers per hour, and you throw a rock out, you add the velocity to the rock. So if one has to account for the velocity of the rock, the velocity of the car will influence the velocity of the rock. Whereas for a train and the sound that it's emitting, it doesn't increase the velocity of the sound wave. The sound wave's velocity is always constant, but the frequency will change. So that's a good way of visualizing how the speed of light is invariant. It doesn't matter, generally doesn't matter the velocity of the source object. And then this will play out in some interesting ways of how it affects the clock. That's the connection I need to make. That's what's a little bit strange. So what some people have suggested is the reason the clock slowdown is as a spaceship is traveling through space, it there's something in the ether that is causing its clocks to slow down. That's a non-standard interpretation. The mainstream interpretation is that time will flow differently, and I personally reject that, but I have to at least state that for completeness. The mainstream will say the time will flow differently, but what I try to point out is just as equivalent to say maybe your clocks just slow down. Something causes everything to tick slower. It's just like if you are if you're trying to walk through, like if you move your hand through the air, it moves relatively freely. Now, if you're going real fast, and the wind's blowing on your hand, like let's say you stick your hand out of the car window when it's going fast, you'll feel that all that resistance. You can't quite move as freely going one direction, and so there's an idea that there's an effect that the ether has on clocks that it just kind of makes it slow down. It just can't move quite as freely. That's not exactly the best analogy, but we can at least show experiments that show this effect. Why it does that, we don't know. So I prefer to say that time is absolute, but maybe the clocks slow down. So the Rovelli book, and I read parts of it, they're trying to argue that time kind of emerges from some sort of physical interactions. We can, I haven't delved that deep into it. But maybe the only takeaway that we could get from this discussion is that we can change the clock speeds. Can the speed of light change over space in certain parts of space? That's an open question. And I've seen some experiments that have, or papers that have tried to argue that if what they call the 0 point energy density is lower in certain parts of space, light will travel faster through it. But these are topics for another day. So I'm sorry I haven't been able to answer your questions very clearly. Physics is very difficult. It's not quite as easy as some of the other things that I talk about, like with proteins.
No, so it was very, very helpful. And you said 0 point energy?
Yes, 0 point energy. There is energy within space. People think space is nothingness, but it actually has something. There's something in it.
Mm-hmm.
Just like when we look at the air, you wouldn't think that there's anything there if it's a clear atmosphere. But when you start moving, you start to feel it. You definitely start to feel the air. And there is something like that with 0 point energy. There are experiments we can conduct. I'm embarrassed now. There's a very famous, Casimir effect. Let me type it in. Casimir effect. And let me just verify it in the Casimir effect. With the C. Okay, I'm going to just put it in here. There's a Wikipedia article that talks about it. Here, Casimir effect. Let me see if I could just read it a little bit. Let me see if I could find something here. There's something called 0-point energy. Hang on. I'll give you another Wikipedia link. I could tell physicists have been updating the Wikipedia articles because they're very well written. Okay, the 0-point energy. This is another link. And don't worry if you lose the link. We can, if you want to talk about this again, we can. I might have to do some serious studying so we can revisit some of these topics. And I may be trying to release a video that will cover some of this. So your questions have been very, very helpful to helping me conceive of a script. So 0-point energy, let's see. The universe can be thought of not as isolated particles, but continuous fluctuating fields. And let's see, vacuum.
That's like ether.
So the empty space of vacuum has certain properties. So they're properties of the vacuum. And I'm not schooled well enough in 0-point energy, but to talk about it, except that I've seen some papers that said we might be able to change the properties of the 0-point energy, and then we can change the speed of light traveling through space if we can change the 0-point energy of space. So there have been some suggested experiments. So how that relates to creationism is if there are some natural changes, if there's some natural variations in the density of the 0-point energy through space, then light can travel almost instantaneously, which would be very interesting in and of itself. Unfortunately, a lot of our experiments are bound to kind of our locality of space, but it could be very different the farther out you go. So there's a lot, what I've thrown out is just a bunch of speculation right now, but I'm kind of excited where it might go because I've seen some experiments that suggest our understanding of physics needs a little bit of an update, and it could be favorable to our understanding of creation science.
So that 0-point energy sounds like ether.
Yes. That's why people get on my case for saying ether, but there's been kind of a revival of the ether because of this idea of 0-point energy. When quantum mechanics began to predict properties of vacuum space. And there's been some excitement that there may be variations in the 0-point energy depending on the location or conditions of affecting space. So there's a lot. We live in very exciting times, even from a secular standpoint. It's very exciting with the discoveries that we're coming up with. And I think even more so, it's going to be exciting for the creationists because anytime we have a major upheaval in our understanding, that's probably going to be good for creationists. And me personally, I'm interested in experiments. So I've been tracking some of the experiments on variability in the speed of light. And there have been a few in the secular world that have studied this. So you could probably tell that I'm one of who believes in an absolute clock, notwithstanding some of the good work. That was a very interesting book that you sent me with Rovelli, the 2 books. Thank you very much for that. That was very kind of you. I just generally think the way we intuitively experience time is probably correct. That we have an idea that there is probably some absolute clock of how everything works. And if we make that assumption, then that opens up some interesting possibilities of physics. So I would say that our intuitive understanding of time is probably more correct than the way that it's described in the mainstream where time flows differently. I would just say our clocks tick differently, but time is absolute. Our clocks just tick differently. I mean, you can you could probably think about this as there are ways we could probably slow down clocks, even mechanically. It doesn't mean time flows differently. It just means your clock is ticking differently. So with that, if we have the idea of an absolute clock, we've had some experiments that suggest that the speed of light may change depending on where you are in relation to the ether and how you're moving through it. So there have been some experiments, and we can talk about some of those too. There have been some people that say, well, the Michelson-Morley experiment kind of refuted that, and some people have studied the Michelson-Morley experiment with mediums other than vacuum and shown that there's been anomalies. So this is a deep topic, but I have to think about maybe how to cover this in a way that's just not too deep in the details. So we'll just see where that goes. So if we thank you for joining me, and I probably have to conclude this this live stream. But if you'd like to talk about this some more, maybe we could. You can give me some emails, and we could think about it, and we can have another live broadcast, because this has been a lot of fun.
Thank you, Sal.
And we can also talk about biology. Yeah, I'm thinking about also having an educational series on biology too. But it's sometimes good to just interact with someone who's just not going through a structured program, like in university where you have to go through all these classes first, then you can start asking questions. It's almost better to get someone outside of the field and they ask questions, because it makes me think a little more clearly, and try to communicate ideas more efficiently. So I still haven't looked in too much into the Kunev experiment, but if you want, we can try to talk. We can have another live stream on that.
Yes.
I'd have to read up to on it.
Biology is more accessible.
Yes.
Physics is very, very, very difficult.
Yes.
Really.
Yes. And so one way I expect that my channel, I'm hoping to build out my channel, is to take questions from people and then try to work on it and try to answer it. So probably some of the easier stuff is going to be in the realm of apologetics and Christianity. I'm going to be trying to do, welcome Nicholas. We see Nicholas has joined us. I'm going to probably try to do a topic on demons and UFOs. Have you studied that at all?
No.
Okay.
I do not believe in aliens.
I don't either.
So, but it will be very interesting.
So let's see. I may have an after show when Nephilim Free has his flood debate, and then Sunday I'm scheduled to talk about protein probabilities, which will be a lot easier than the discussion we had today. This was a really hard. This is a really hard topic. So, anyway, God bless you, and hopefully we'll talk again, and maybe I'll see you. My talk is scheduled for 9 p.m. Eastern time for protein probabilities on Sunday. I hope you can make it. If not, I hope you can at least watch the recording.
I will probably make it.
All right. Well, I look forward to seeing you.
Okay, so thank you very much.
Yes, and if you have other questions, I'm sure we could start another live stream and talk about it. It's a great way to build out our channel. I'd like to thank all of the viewers, both live and who dropped in and who are watching us through recordings. So take care. God bless you.
God bless.